Alright, here's our video today. Phosphine and life in the clouds of Venus. Potential life, right? We haven't found life in the clouds of Venus, but phosphine may be a good indicator that there's perhaps, and there's the big word perhaps, there could be life in the clouds of Venus. Now, this is just an artist's rendition of what cloud cities on Venus could look like. There's been speculation that NASA wants to make cloud cities. Of course, we probably don't have the technology yet. Anyway, because on the surface of Venus, now remember, Venus is the hottest planet in the solar system. It's hotter than Mercury, even though Mercury's closer. Venus is going through, or not going through, it has a runaway greenhouse effect. 98% CO2, carbon dioxide, is in the atmosphere. So life on the surface of Venus is impossible. You know, you're looking, let me write this down. You're looking at temperatures that can go above 900 degrees Fahrenheit. 900 degrees. With pressure, think about the pressure. It's 92 times greater pressure than Earth. Greater pressure. Just think about that. If you landed on Venus, which no one's going to land on Venus. I mean, we have spacecraft that landed on Venus. I'll talk about that in a minute. But 92 times greater pressure than Earth. So if somehow a person landed on Venus, they would melt and blow up at the same time, right? The pressure is just enormous. Now the Soviet Union no longer exists, right? The old Soviet Union that used to have Russia and Ukraine and Belarus and so forth. The Soviet Union landed spacecraft in the 70s and 80s, and they had the first spacecraft was Venera. That'll be the program, the Venera program. So the Venera 7 landed in 1970. And when it landed, it lasted 23 minutes before being crushed. And then there was the Venera 9 and 10 and so forth, and Venera 13. I have a picture of Venera 13. Let me get that for you. All right, so here's the Venera 13. Landed in 1982. Let's put that in 1982. Launched in 81, landed in 82, and it lasted longer than Venera 7. Lasted 2 hours and 7 minutes before being crushed. So there's the surface of Venus that they got. Extremely hot, extremely, a lot of pressure, I should say. Now Venus is a little smaller than Earth. If you looked at them, you would see that they almost look like the same size. And we used to call Venus, we call Venus our evil twin, right? Because they think maybe 2 or 3 billion years ago there could have been water or oceans on Venus. They're still debating that. But they know today that there is water vapor in the clouds, and we're going to be talking about the clouds of Venus, because what they found on the clouds is phosphine, and this is the real thing, phosphine. And this is very interesting because it's very hard to make phosphine without life. Not to say you can't do it, but it's very hard, and I'll explain that. So, phosphine. And what you're looking at here, this pH 3, right? It has, you can see it has hydrogen, has 3 hydrogen molecules in it, atoms in it. So we're looking at phosphine gas, and it could be made abiotically without life, or biotically with life. But the thing about phosphine is I'll write it over here. It's strongly, on Earth especially, strongly, not just associated, but it's strongly associated with life. Strongly associated with biological, which is life, biological processes. Well, processes. Sounds better to say processes. So on Earth, for example, phosphine is made biotically with bacteria and fungi. And on Earth, phosphine is not produced by non-life. So let's clear this out. By the way, on the left is what they thought Venus may have looked like maybe 2 or 3 billion years ago. And right now it's a living hell. It's like an oven. More than an oven, right? But anyway. So on Earth, well, let's just use this picture back with the cloud cities. So on Earth, put it on Earth, phosphine, talking about phosphine. Phosphine is a byproduct. It's a waste. It's a byproduct of anaerobic, not aerobic. We go through aerobic respiration, but anaerobic, which some bacteria and fungi go through, anaerobic. Get that spelled in there. Phosphine is a byproduct of anaerobic biological processes. Fancy words today. So, in other words, by bacteria and fungi and other microbes, they produce phosphine on Earth as a waste product. So, it could happen abiotically, and let's look at that. And again, biotically is life, biotic, life. Abiotic is not life, non-life. So abiotic production of phosphine could happen, but on Earth it's very difficult. It's extremely difficult to make phosphine without life. And so we have to ask ourselves, do the clouds of Venus have those conditions, those abiotic conditions? And let's look at that. So in order to have those conditions, we'll look at the abiotic conditions. Non-life, just to make it simple. Abiotic conditions. Put a little arrow over here. I'm getting into blue skies over there. And we'll just use that color. So you need high temperature. And you say, well, Venus has high temperatures. Well, you need high temperatures above 600 degrees Celsius. And that's well over the temperatures of, well, not well over the temperatures of Venus. Venus is close to that. So 600 degrees Celsius is about 1,112 degrees Fahrenheit. So Venus doesn't get to those temperatures. Earth certainly doesn't go through those temperatures. You also need pressure, which Venus has, but you also need reducing agents. Reducing agents. What are these? Well, let's explain that. Reducing agents, especially hydrogen or methane, which Venus, by the way, has very small amounts. And there's no evidence that it has methane anyway, but you need reducing agents because what reducing agents do is they donate electrons. So reducing agents, say hydrogen or methane or both, they donate electrons. Case of hydrogen only has one electron anyway. So let me get a clean page here. Alright, so the reducing agent, we'll say hydrogen, especially two atoms of hydrogen, H2. So it'll donate electrons. Donates electrons. And it has to donate these electrons. That's why they're called reducing agents, because they will donate electrons. So they have to donate them to compounds. Donate electrons, forgot the two there, to compounds that are phosphates in order to make phosphine. So let's look at the process. So let's say, and by the way, those phosphates could be calcium phosphate, for example, calcium phosphate, which, if you guess, has calcium phosphates. So calcium phosphates would be, there's calcium. That 3 means, so there's 3 calcium phosphates there, and then PO4 is phosphine, right? So you need these phosphine and calcium. You put that together, and you'll yield what we're trying to get, right? So, and let's look at another one. You can also have iron phosphates, for example. So let's look at a formula. So let's say we had iron phosphate. So you would need 2 iron atoms, right? Plus the phosphine. You need 4 of those. This is, well, this whole thing right here is iron phosphate. Plus you need the hydrogen, right? You need 6 of the molecules of hydrogen that are 2 in them. Two hydrogen atoms together is 1, and you need 6 of those, and it will yield, with the yield sign, it will yield, and this is what we're looking at. This is what we talked about in the video, and this. So what do you notice? What do you notice? So what you notice is this is phosphine. This is phosphine. If I can get my O working. And this, you notice, is water. So it makes water, and there is, I should say, water vapor, traces of water vapor in the clouds of Venus, and they're still studying that. So, I mean, phosphate, phosphine, phosphorus, you can all get confused on it. So, back to the calcium phosphate to make sure you're clear on this. This is calcium and phosphorus, right? And together they'll become a phosphate. And if you put those together in the formula, you'll get phosphine. So phosphine is the biological marker. It's a big indicator of life. Back to our cloud city. Perhaps maybe one day we'll have that. So here it is. Venus does not appear to have the conditions to make phosphine. Anyway, so first of all, its atmosphere is very thick. It's CO2 is in its atmosphere, so it perhaps has traces of hydrogen, or traces of methane, but just not enough. And the temperatures, though they're high, the temperatures are very hot. They're just perhaps not hot enough, and the pressure's perhaps not hot enough for abiotic processes to go through. So the question is then how is this phosphine being made? And then again, there's speculation that there must be bacteria perhaps in the clouds. So we know there's phosphine in the clouds, and though there have been debates on it, that perhaps it's not phosphine, but there's more and more evidence to consider, and a lot of scientists now think there is phosphine. So the question is, how did it get there? Something to keep an eye on as we get more information, and that's our video today.